So, hello and good morning, everyone. My name is Jordan Donnelly, and myself and my team are here once again to talk to you a little bit about our project, Home Automation for the Visually and Hearing Impaired. So before we really go into it, this is just a brief breakdown of what we're going to talk to you about today. And like I said, my name is Joy Lynn. I majored in computer engineering here in Manhattan, and for this project, I was a team lead. I focus primarily on software development, computer vision, and research and development. And I'm going to hand it over to Jamar.
Hi, I'm Jamar Lewis Ortega. I'm an electrical engineer, and I work primarily with hardware, specifically RFID and device reliability.
Hello, I'm Mark Saglambini. I'm a computer and electrical engineer. I've been working on hardware and software for this project. I've been doing mainly the iOS application and server application, as well as camera systems.
Good morning, everyone. I'm Patrick Squiet. I'm an electrical engineer here, and I was focused on the hardware side of things in this project, primarily the electronics and the sensors.
So as we know, technological automation or tech automation is such a big part of all people's lives, supplements the daily life of any individual. But with such a large portion of our population being people with hearing or visual impairments, we sought to create a solution that would heighten their daily life by creating independence through supplementing their visual and hearing impairments with other senses via this kind of modular system that we created. So this modular system that we sought to create was based within an iOS application that made daily tasks, such as appliance control or home navigation, easier for the hearing and visually impaired. So there have been many solutions in our research we found that offer assistive wearable technology solutions and data fusion algorithms within, as well as wearing multiple sensing devices on or around the person. And while this was the base framework for what we moved forward with, we saw that it caused functional limitations in some aspects, as well as less accessibility options for the given user depending on their impairment. And this is a bit of foreshadowing, but in our research, we also found a lot of different image processing options. So for our system in particular, we went with a motion detection camera algorithm, and we wrote this in C++. So as is the case for a lot of imaging processing algorithms, we made use of the low pass filter, as you can see in equation 1. And in its second equation below, you can see in its discrete differentiated form. So with this, we then use downsampling, and downsampling allows us to reduce the spatial resolution of the video feed and compare it frame by frame. And in this, we can detect motion as one frame, and the pixelation in one frame to the next changes.
So there are many different smart systems out there. You know, mainly you would see things like the Ring, a Nest doorbell, or like an Ecobee thermostat. We have a picture here of a Simply Safe alarm system. However, all of these devices, if you do have all these in your home, they do require different applications for control. They usually don't work with the same type of smart thing like Alexa, Siri. Sometimes some do, some don't. We aim to solve this problem, creating one system that would communicate through one server and one application, making everything very streamlined and easy to maintain. We did this through a user-friendly interface, making everything modular so things can be swapped out. So in the United States, 2 to 8% of the population is blind and or deaf. This shows the strong need for a system like this that can help those people with daily tasks that a lot of people find you know, and they take for granted in this country. So we aim to do this through our universal system with an easy installation. Once it's installed, there really isn't going to be much tampering with it. It's kind of just works from there forward. There's going to be that one application that has the haptics and sound feedback. So any notifications that go to the application will give a vibration that's pretty prominent. That will be aimed for those with a visual impairment or a audio impairment as well. And then also there will be Siri implementation for those with the visual impairment, and there will be blind control and things like that around the home that are there to help people with privacy and just keeping everybody safe in a situation where it may not be so easy for them.
In choosing our project, we contemplated approaches like a fully on-person wearable device, a system focused with strictly external sensors, and a system that incorporated both. After comparing the cost, feasibility, and ease of use of each, we decided that a full system with both on-person accessibility and external sensors would be the best option. Here we have the HP matrix for system requirements. There were requirements we want to focus on were easy use, high accuracy, cost effectiveness, and low response time. This is our objective tree that shows a breakdown of each category that was previously mentioned, and you could see that accuracy is further broken down into motion detection, voice detection, reliable RFID, and that's where we're going to spend most of our time in this project. So our engineering requirements are summarized as reliable motion detection, reliable RFID, low response time, effective haptic feedback, safety, and seamless device communication. And this is our trade-off matrix that compares that to the marketing requirements to emphasize the give and take we need to consider.
So our system, as I mentioned before, it has multiple wireless nodes. Every node is wireless and connects through the local network, even through the internet, with a Raspberry Pi-based server that's running in the home. All of these devices communicate with that, including the iOS application, then sends and receives data from that server. That user interface that you would see on the iOS application keeps everything streamlined, trying to make it as easy as possible for anybody to use the application. Each device has its own function and then relays the necessary information to the server. And then the iOS application is constantly checking the server and receiving those updates as they're pushed through to give the user the updates that they need, either haptically or visually. Here you can see a behavior diagram of our system. On the left, you can see the user sending and receiving information from the iOS device as they use it. That would be through the iOS application. And then on the server, we have what's called MQTT. That is our communication protocol that then sends and receives data from all of the different subsystems, like the contact sensor system, the RFID scanner, motion detection, smart blinds that we have, and our real-time camera system that we have. All that information is relayed through server, then back to iOS device, and then ultimately gets back to the user, so they're able to control and see all that information right there at the tip of their fingers.
So here's the functional decomposition of the system. This is the big picture with the inputs and outputs of the system. So you can see some of the inputs. We have an image that goes to the motion detection, a voltage input, which goes to all the sensors. Location information goes to the RFID, and door state information will go to the contact sensor. And all that information goes to the Raspberry Pi, which will send it to the iOS device, which will result in haptic and audio feedback alerts on the user's device. Here you can see this is the level 0. This is, you can see just the real basic big picture where you can see location data, door state information, visual information, power supply as inputs, and the outputs is the haptic and audio alerts. Here we have the functional decomposition of the server itself, where we have the Raspberry Pi, which runs the server. It's got a network input, which is a Cat5 or RJ45, a 12-volt DC input and network outputs, and the MQTT, which will take in the network subscription posts and will send out posts to the devices as well. Here's the iOS device, which inputs network packets and outputs network packets, which is just communicating with the network and the system itself. And the application itself takes in the data from the devices, which goes to the server and will send back data to control those devices as well. Here's the motion detection system, which will take in the light signal or the visual signal, as well as the DC power, and will output motion data, which is sent to the server on whether or not it detects motion. Here's the haptic and sound feedback, which will take in the network data from the server and will send out a audio or vibration signal to the user's device.
So here you can see the hardware implementation for the blind system. On the left here, we have a hand-drawn image. On the top left, you can see some measurements taken. That's the inside measurements of a normal blinds that I had in my home. And then on the right there is also a servo, and that has measurements there for the servo. On the bottom of that, that's a wiring diagram for the blind system. On the top right, using Autodesk Inventor, a CAD drawing was made to hold the servo inside of the blinds. And then on the bottom there is an adapter to go from the servo to the tilt mechanism inside the blinds. On this slide here on the left, you can actually see the servo with the adapter on it inside the blinds, sitting inside a 3D printed mount. On the right are all the different components that are used and the wiring that was needed to get the blind system connected up to the internet and to our system.
Here we have the hardware setup of the RFID RC522 sensor connected to the ESP8266 microcontroller. In a full implementation, this would also be connected to the voltage regulator that Patrick will speak to.
The image on the left is the voltage regulator, which is the small component, which looks like a transistor. And that has 3 pins. One is straight to ground. Then the other 2, we have a voltage input and a voltage output pin. The voltage input pin takes the voltage from the wherever we get it from, which is a battery, which has a voltage too high for the chips itself, and then it will step it down to a safer voltage for the system. And you can see the voltage input and output pins both have capacitors, which are connected to ground as well. On the right side, we have the actual contact sensor itself, where we can see we have the voltage output pin, which is the red wire, and the green wire, which is the ground, connected to the board, as well as the contact sensors wires are connected to the board. Here's the ESP32 camera chip. This is the motion sensor. On the final implementation, we would not need the ESP8266 chip, which is the other chip connected to there. That was there so we could write data onto the chip and write the code onto the chip. Since this does not have any USB inputs to put the code on, and this would also be capable of using the voltage regulation system in a final implementation. Here's an implementation test we did showing the contact sensor connecting to the server, as well as using the voltage regulator for power. You can see the first thing we did was making sure the code would be able to be written onto the board itself. And it could compile, and then we could test if the server would recognize the sensors, if we get notification on the server that it has connected, and if we can receive notifications of the contact sensor's state and whether or not a door is open or closed from the server itself.
So here you can see our software information. Mainly, this is the iOS application. The application was coded in Swift using Xcode, and then uploaded to a iOS device, my iPhone in particular, and then also our teammates, and as well as using a simulated one here. On the left, you can actually see the splash page that is loaded when the application is first launched. Then it brings you to the home page with the next image there with the image of the home in the background. And then the second image from the right shows you what happens when you click on the home controls. That brings you to where you would get the information about the home in terms of status of different things around the home, as well as control for the blinds and the camera feed button to show you the live camera that's in the home. And then if you go to the settings page, it just has some user interface stuff there, as well as settings for the notifications on the device. Here is a flowchart showing the application going through the process of receiving messages and then categorizing those messages in terms of contact sensor, object location, motion detection, and then updating the necessary variables inside the application, and then going back and just waiting again to hear from new messages and allowing for updates through the app, and then sending those notifications that are needed to the user. And then here we have a test that was performed by Joy back in February 20th. This test was to control the blinds. Now, Joy was not on my local network. I do have the blind system here at my home with the server. She was able to use the iOS application to control the blinds remotely over the internet, showing that there was proper connection through the internet to control the different devices in the home.
Here's a unit test that shows the testing of the tags and cards for the RFID reader at different distances, ranging from 1 centimeter to 4 centimeters. This iteration table shows the 10 iterations of the previous unit test to show the reliability of the sensor. And this histogram shows that the RFID reader is reliable to 2 centimeters at 100% rate. We can also see that the card has more range than the tag. The overall range is low because we bought a low range sensor to save on cost. In a full implementation, there would be a much larger range. And then here we have a scatter plot that shows the response time in seconds per number of messages on our server. We tested a higher amount of messages than really required and came back with relatively random data. All in all, however, we're content with the response time in the prototype.
Here's the acceptance test. This was the final test that we conducted to make sure the system operates as a whole as we hoped and expected. The first thing we did is make sure the components could connect to the server. We could open up the live camera feed. Our sensors, when their values change, it actually changes the values on the server itself. And this data can be sent back to the app, and you can actually see that the data has changed, and that the blinds could be controlled by the user using the app as well.
And then here you can see our project timeline. So the bulk of our time was spent in our modules, our power consumption, our server, iOS, and camera. You can see our milestones that we hit back in December so we could move forward. And ever since about February, we've been integrating and testing the full system. So as we are marketing this particular system to visually and hearing impaired people, they are fairly reliant, if not completely reliant, on the system at times for their independence. So this is something we took extremely seriously in our studies. So accuracy, both temporal, both time and in functionality, was extremely important. So we risk the integrity of our system if we don't meet these. And our major risk analysis was the safety of the consumer.
Here's a chart of our cost estimation for the project. We are currently under budget at around $190. Because we downgraded to a low range RFID sensor, we were able to gain some wiggle room in our budget.
So here we have the system demonstration. Before I start the video, I just want to let you guys know that this was performed over a Google Meet. All of us were at different locations, all connected through the internet to actually perform this demonstration with different devices at different locations, communicating all through the internet. And you'll actually see the Google Meet in the background in certain parts of the video, and then we zoom into those locations. So here you can see the iOS application, Smart Home, is going to be loaded, and then that's the splash page that opens up, and then it brings you to the home page here. We're going to go into Home Controls and take a look at the live camera. So the camera feed button is going to be clicked, and then this is the Google Meet in the background that I was talking about. You'll see my view here on Google Meet will get zoomed in, and you'll see the application on the right and the live feed there updating in real time. We actually go through step by step all together here in one shot to show everything working. Then we're going to go to talk about the door sensor here and show that. So we have Patrick on the top left that we're about to zoom into, and that is showing the contact sensor there, changing the front door status on the application as the contact sensor closes and opens up. That shows that we were able to take the readings of doors and windows around the home and implement that right into the application. Then we have object tracking. So through the RFID tags, this would be located in the master bedroom, and then that tag would be on a pet, and then the key would be on your keys, and then you'd be able to determine when those things go into that room. This is another scanner for RFID. This would be located in the doorway of a bathroom. And the same idea, when the same tags go over this, it would update to let you know that they're in the bathroom, and you can see that that is working there. And like I said, this is happening completely through the internet. The server is actually not even on the same network right now as these, and everything is updating in real time. Next, we're going to take a look at the motion sensor, which Patrick has on the top left. And you'll see that he moves his hand over the motion detector, and the kitchen motion sensor goes off, showing motion detected. Once he moves his hand away and it gives it a couple seconds, the motion is no longer detected. Here you're going to see our automated blind system, which you'll see behind me. And we got the blinds behind me. Oh, yeah. That was cool. We can close those. So you can see the blinds behind me were moving when we moved the thing there in the app. And then we have settings in the app, which we're just going to show putting in the name and then how the user interface changes and just welcomes the user and basic things like that. We wanted to make our app friendly and easy to use. And that changes based on time of day as well. And then we're going to show Siri control here. Open the blinds. Where is my pet? Or status.
All right, so here we have an example layout of our design around the home. Every home will have a central hub connecting all components. Ultimately, the layout is up to the user, but we recommend contact sensors on all doors and windows. And then the motion detection and live feed cameras can be implemented wherever the user pleases. And then here you can see the RFID sensors on each doorway. Again, that's because the low range RFIDs sensors that we used. In a full implementation, we hope to have a long range RFID sensor located in a central location on the ceiling of every room. And then these are the specific Wi-Fi and RFID standards we have to follow in accordance of IEEE. Ethically, we also followed IEEE standards to prioritize safety and privacy for users.
So as you can see, we've come pretty far from the beginning. We have definitely learned a lot about programming in general, Arduinos, and we have created a fully functional server that is based in Mark's home, so we can all connect to it. We have an iOS application fully going that we can add to, subtract from when needed. We have mastered our efficient power consumption, which was a big issue when we looked into other problems. Other solutions, always that on-person device. That was never something that they could really keep on them, but your smartphone is constantly on you, and the Patrick's power consumption works seamlessly with our other modules. So if we were to keep going with this, what we've come to know and love about this project so much is that you can only keep going. It's modular, you can keep adding, and you can put as many, as you can see in the map that Jamar just showed, you can put as many or as little as you want within your home. If we were to keep going, we would like to increase the accuracy and efficiency with higher quality RFID and contact sensors, as well as cameras with higher resolution. And we would like to further our algorithms, maybe go in the direction of facial detection, or I've seen things with heat sensors too for body versus object. So another thing we did have aesthetics for our particular casings, but we would like to make them more suit to our liking. But that budget, constrict us a little bit on that. And then we would like to increase the haptic and sound reliability and move forward with a more full and robust system, which is fully capable, and we hope to do so in the future. And the next two slides are just a bit of our reference points. And if anyone has any questions.
Perfect. Thank you so much. It was a very interesting topic. If anyone has any question to this team, please go ahead and unmute yourself, please.
Well, if not, thank you guys so much for listening to us, and we hope you enjoyed our presentation.
Thank you, everyone.
Okay,
Thank you.
you're welcome. So now we will be welcoming the next team, Franklin and Magdalena, Selby, and Eliana, for presenting their topic, Flight Support Autonomous RC, Playing with Payload Release. Please share your screen.